it's quite late, so I won't talk too much. So yeah, implementing the built-ins. I think I'll actually have a separate file for... Okay, so what I don't like is that the ArrayLen, and I mean later on also ArrayGet, ArraySet, ArraySlice, FilterArray, and so on. I don't want to copy the code everywhere that you call this function. Instead, I just want to have, you know, one call to some ArrayLen function and one call to some ArraySlice function and so on. So let's do that. Array ops for operations. Built-ins. It's going to be similar to these. Was an array types. Array, this right here. Let's just do it type.array. checking that the index is within bounds. Nice. Interesting. Well, descriptive. This is interesting. Hang on. Nope. Sure. Why not nest them, right? That is nice. Clean. Ooh, yeah. This is where the optimization comes in. If the reference count is 1, then we will just mutate the item in place. That's unreachable. Yeah, I guess we don't really need that. Yeah, because this doesn't contain anything. So we already have 2 branches here. Yeah, let's just return nothing, I guess. overwrite the previous item. So we load the buffer item. Hang on, not from the index, but from the offset, which is this one. Now, in this case, we need to copy. names, I guess. Actually, I think a better primitive than filled array would be generate array. With a slightly different signature. Generate array of some size. And then a generator that just takes nothing. Oh yeah, it takes an int and it produces a t. Hell yeah. into something. Yeah, this. Yeah. These are not recursive, so yeah, no need for that. Again, doesn't hurt. Plus I'm not sure about the deep and drop, whether they may need to call these functions. Well, better leave this in. Okay. Okay, buffer pointer is, well, builder.new buffer. Fair enough. We've literally created a new buffer with some len. Now we want to fill that buffer. This accepts. Oh, in it. Yeah, sure. Now a buffer pointer, which will be a pointer, a length, which will be an int, a cursor, which will be an int, and then a generator, which is pesto lambda type. Why doesn't that work? Well, never mind. Okay, so here we go. The length, cursor, and the buffer pointer. Beautiful. Alright. Then we just basically switch. If the cursor is less than the length, and then we'll set the item at that position. Well, we'll first call the... Oh. Arguments being well, a closure being that, and that returns us an item. We store that item, and then we are basically done. Yeah. Oh, and I do need to create a new builder here, similar to this. If they are equal, then we will just do nothing and be done with that. This is greater. Yeah, that's basically unreachable. Yeah. All right. Oh yeah. After storing the one item, we also call ourselves and that returns nothing. Alright. that is a new buffer, and then the array is just a struct. Oh, it's just called buffer, which I guess is the same name for that. The switch can also figure out its type, can't it? I think so. In general, a lot of these functions could have more guardrails, I think. Oh, look at that. Oh no. Yeah, okay. Yeah. can figure that out. Here we go. Oh, hang on. That actually makes sense, I think. Well, okay. Not so crazy after all. Okay. Yeah. to update this, I think. Yeah, let's just go through this and see. so in general, I don't like this kind of rigid distinction between built-ins and instructions. And we have built-ins, the kind of functions that you can call that magically exist in the built-ins module, and then instructions that the VM actually implements. This was the initial idea, but in reality it's more like we have built-ins, and then some of the built-ins, they get desugared pretty early in the compiler pipeline, like for example the call operation, which just directly becomes a normal lambda call, or now the array operations, which actually get desugared into more fundamental operations that operate on buffers. Some of these operations, like the type operations, they get removed during monomorphization. When functions get specialized for concrete types, there the type of function is just replaced with a type literal. And the type info function, well, the type has to be compiled unknown, and it just gets replaced with the type info struct instance. So these built-ins, they're not like a fixed set of functions that then, you know, where there's a hard distinction between built-ins and instructions. Instead, we have a set of built-ins that the language provides, and then these are kind of trimmed down as we go through the compilation pipeline, which makes me believe that we actually want to put built-ins into each of the compilation stages and have a separate concept of built-ins in each of these. But not today, because it's pretty late. So yeah, see you and then sometime. Alright, so refactoring built-ins. In the toast, we don't have any sort of built-ins. The toast doesn't know about built-ins, it's just the parsed syntax tree. Then in the egg, functions get resolved, and that is where built-ins come into play. So these are actually more like egg built-ins. Let's maybe, let's just move these somewhere into the egg. So here's the egg. Do we reference built-ins here? Yeah, matching built-in. Look at that. Yeah, we want exactly that. Matching built-in, and then this is an egg built-in. Clean. And these here are just, well, the printing I'm going to keep that here, but the others, they are really more part of the compilation than anything else. Alright, so in the something to egg, toast to egg, yeah, when looking up a function, I think here we'll also have the code that has the built-ins. And yeah, built-in in here just means egg built-in. And let's re-wrap these. This is fine. Alright. Is the signature used? I'm not sure. Types, same thing by the way. Plum type. There is no coherent concept of a plum type. Yeah, let's just see where this fails, and then we'll get there. Right, built-in. Yeah, in the egg, this is supposed to be an egg built-in. Let's move that to the other right functions. Then in compile fun, yeah, we do use the signature here. Okay, so that that's in 299. This would be egg built-ins. Yeah, okay, you know what, let's move this list to here, because that needs to be kept in sync with that, you know. Alright. Yeah, generate array doesn't exist. That's true. And putting to pesto, yeah, okay, but they get their own kind of built-ins. So once we are in the egg, that is converted to the yogurt. And at this point, I think already some built-ins disappear. And actually, I believe, yeah, yogurt already has its own concept of built-ins, which is, yeah, exactly what we want. Okay, so, hang on. Got up early today, that's my alarm. Yeah, yogurt built-ins, we already have that. Then yogurt to pudding, this is, stuff failing, pudding to pesto, okay. Yeah, yogurt to pudding, and the pudding, we have well, we'll just have a lambda call or a pudding call. Yeah, okay. And then we have a pudding instruction. Instruction coming from here. So let's actually move that here and rename that to pudding builder. Yeah. And also let's use a similar strategy to what we did in the egg on the yogurt. Yeah, where we have just a call with a callee and arguments, and then the callee can be any of these. So here we have a pudding call with a pudding callee and arguments, and the pudding callee can either be a lambda, that would be basically this lambda call right here. It can be a function, then it would be this call, or it can be a built-in, which will actually be a pudding built-in that would be similar to this pudding instruction call. Alright, and then in here these get merged to just the one call. Clean, yeah. And then this one gets moved somewhere down below. Writing pudding. Yeah, we have the call. Not for these. We print the callee. And then, similar to what we did in the yogurt, we just have this one, a pudding callee, can be printed. If that's a lambda, we just print the ID. If it's a function, we just print the ID, the signature string. If it's a built-in, then we just print the built-in, and we then no longer need this one. Alright. Yeah, pesto. Let's see what goes on there. And what's the next step, by the way? Putting to pesto, I think. Yeah. Alright, so in the pesto we have operations. Yeah, and here we have pesto call instruction. I would say make it similar to the other two, right? Have something like this. Yeah, just have the putting, I would say, the pesto call with pesto callee, and that can either be a lambda yeah, maybe let's not make it like the call calls some function. The call indirect also calls a function. It's not that the callee is something different. They're more like different kinds of calls. You know, one is direct, one is indirect. Yeah, let's keep them separate. Sure. And let's rename this to call built-in, and then in here have a pesto built-in. Nice. Which will be any of these. I will just rename this to call fun. It's fine. Pesto call built-in with a pesto built-in. Sure. And then what is a pesto built-in? Well, it's any of these, except the array ones. They no longer exist because they are not as fundamental as the other ones. So that has been, you know, kind of lifted into some other stage. All right. Yeah. That is clean. And here we have call indirect, and we have call built-in. Just like that. Okay, then we have the builder. Putting the pesto builder, right? Yeah. Where we can call a built-in, which would be a pesto built-in with some arguments. Just like that. And then you get the pudding. We have this pudding op.lambda call. No, we just have a pudding call. The callee is, well, actually not sure. It's pudding callee dot lambda of the lambda, maybe. Yeah. And then this, here we have a callee, which is a pudding callee dot fun of some fun. Amazing. Yeah, then for built-ins we just have the pudding op dot call with the pudding call where the callee is a pudding callee.builtin of this. Nice. That's pretty cool. Yeah, here we go, yogurt to pudding. Oh yeah, these are not instructions, these are just pudding built-ins. I mean, these are literally the same as in the yogurt. Ah, that's fine. Alright, then in pudding we have 102. Oh, in pudding. Well, true. Oh yeah, also let's directly do the adjusting of replacing filled array with generate array. Yeah, in the egg and also in the yogurt. And then in the pudding, and the pesto that's removed already. Alright, so in pudding to pesto, we don't have lambda calls. No, we just have calls. Yeah, so yeah, we'll create the lambda. You know what, let's just switch on the callee, I guess. Yeah, if that is just a function. Yeah, this basically stays the same among all. Yeah, if that's just a function, then we do builder.call with the function and then a struct representing the arguments, which would be a builder struct. Yeah, if that is a lambda though, then we'll get the lambda and the closure pointer and the body pointer, and yeah, we've constructed the arguments already, and now we also put the closure in there. Then we call that. Nice. And then, last but not least, in the instruction call, built-in call, this is where we switch on the built-in and do different stuff. Alright, we have this instruction of add ins that results in, well, the pesto built in. Yeah, let's move this inside the individual branches. I think that's a bit cleaner. Just like that. All right. Yeah, that would literally be called at once. Nice. Yeah, then this is just the pesto built in. Clean. Yeah, here the item type, what is that? Well, that is fun.dag.type of the generator. We know that's a lambda, so we can unwrap that. And then we look at the return type. That is the item type. Yeah, then ArrayLen. Well, that is just that. Yeah. Array get, very similar. Array set, very similar. Array slice, yeah, gotta do that. Okay. Yeah, and then here we do call built-in with the built-in and the arguments. Nice. Now let's just see where the compilation fails. Already in the egg generate array, there should be a variant there. Yeah, then in lookup. Almost. good. Not sure what's going on there. You're putting. Oh, I see. Next compiler stage. Nice. Okay, yogurt pudding works. Now pudding to pesto. And the build. Oh yeah, this is called built-in using pesto built-in dot compare ends. Yeah. Nice. Then putting to pesto. Yeah, we already do that here, wrapping that in an actual struct expression. Yeah, not call that lambda, but just lambda. Then this does not work because it needs. Okay, so this is reference, I get that, but also I think this needs. No. Hang on, how does call work actually? Oh, I think that works, yeah. I was wondering, like, this needs a callee, not something else, but yeah, in the pesto we no longer use that pattern. Then array build-ins to the core of this kind of video that kind of got out of hand, maybe. Store buffer item with, oh yeah, we don't need the type anymore because that's inferred by the item. Clean. Then in the builder, in that exact same store thing, we just have the pesto store buffer item and the buffer pointer field is missing. Yeah, no, that's called the buffer. Yeah, here. Yeah. Yeah, then in the builder, this is supposed to be the pointer. The pointer, the buffer has to be the pointer. Has to be a pointer. Yeah. Then you broke 3. Zero doesn't exist. No, that's just builder int 0. Nice. Yeah. Array build-ins going all over the place. Duping some item. going on there? Yeah, it needs a pesto. Yeah, that needs a reference to one. Sure, we can do that. Oh, we could just give a reference in there, I think, because it doesn't store that. It only uses that temporarily during the call. It doesn't store that somewhere. But those are the kind of things that are best not write brittle code, you know. Putting to pesto. Oh yeah, this doesn't exist anymore. This needs to be desugared. And I mean, actually, array slice is pretty simple. Pesto op only has these variants. What do we have here? We have call instruction of some call. Not a thing, apparently. True, because this is now called call built-in. Look at that. I am printing a pesto built-in. I guess that would be similar to printing pudding built-in, which also doesn't exist. Let me guess. Nope. Oh, it's just built-in debug. Yeah, I think that's fine to do here as well. Oh, that compiles. That's cool. Let's see where it fails. Oh, damn. Actually, like the compiler fails, not a compiler internal error. Better than I expected. Oh yeah, filled array doesn't exist. Well, instead we have generate array that takes an int and, well, a lambda that takes an int and produces a heap. Let's copy that signature and move that here as well. Boom. And then in array, yeah, we have this generate array thingy. Clean. Yeah, exports don't currently work, so we can't just import anything. Alright. Yeah. That is true. So this would be, could say generate some int, and then this is a lambda that accepts an int, and it will just returns that. So this should be an array containing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Something is messed up. Let's see. Filled array in the list module. True. The list module uses arrays heavily. So it should use generate array. Yeah, generate array length 8. And the way to generate an item, of given an int, we just return the A item, the fill item. Filled array. Only used here. Yeah, so let's generate array, new size, and then instead of copying and moving and copying an item, the same item all over the place, and then copying the original array, we can just do, given an index, which is an int, we'll actually do list.array.len. We copy the entire array. So we'll just do list.array.get maybe of that index. Is there an else? I hope there is. On Android, probably. Else would be so much cooler. Yeah, if there is nothing there, then we just put the item in there. Clean. Yeah, I get maybe. Oh, for the array t. It does sound useful though, so let's add that. So given an array and an int get maybe returns a maybe t. The way it does that, it just checks, does 0 to array.len. Does that contain the index? If it does, then we just do a regular array.get with the index. If it doesn't, then we'll return none. In this case, actually, that is some. Yeah. And we'll need to import that in here. So get, but also maybe get, and inside the array we'll need the 2, which, hang on, that should exist. I think. Oh no. Like that. Contains is not in scope, that is also true. I think that's defined for a range of int and an int. You may need to adjust that. True. So we have maybe. Alright. Alright. ArrayList. Yeah, and here we'll do the get maybe on the array. That does seem correct. List.array.get maybe. Boom. Yeah, that was this one. Array of t and int. Oh, maybe get. No, let's get maybe. And it would have actually failed if we tried to use that, so. Well, yeah, unwrap or. Need that from maybe. There's unwrap, there is no unwrap or. But I think like a much cooler name for that would be else. You know, we have some maybe t, else, and then the default value. That is clean. So let's just import else that takes maybe t and the t. Oh, look at that. We have an unwrap or. Yeah. Get maybe the index, else the item. Nice. Oh, this is actually really cool that we kind of catch these errors. Yeah. Okay, so in the builder, there's something to pesto when compiling generate array. Now let's look at that one. Array built-ins, compile generate array. Yeah. Let's just go through this. We create a DAG in the builder. This accepts a len and a generator. The len is an int. Generator is a pesto lambda type. Yeah, we get those out of the arguments. We allocate a new buffer of the item type with the length. Let's see. New buffer fails. And we only call new buffer in here. Alright, I guess. New buffer of item type dot to pesto, and then we have the len, which is the len parameter of the builder, of the args, which is the builder param, which we pass in here. That is definitely a pesto type int. Let's look at new buffer. Over here. Oh yeah, no, that doesn't check if that's an int, it checks if that's a pointer. Yeah, I think it's cleaner to put the or on the new line, maybe. Not entirely sure about that. Alright, yeah, the compilation up to this point works. So let's have a look at that. We have our main function. What does it do? It creates a lambda that creates an array containing the items 0 through 9. Alright, so it just ignores the argument, that's fair. Then it creates a 10, that is the length of the array that we want. This is a closure for our lambda that we create, the generator. So we create an empty struct, the closure, we put that on the heap, fair enough. Then we get a function pointer to the lambda body, and a function pointer to the function for freeing the closure, this one. And then this is the actual lambda, consisting of the function pointer for the body, the function pointer for freeing the closure, and a pointer to the closure. Nice. Then these are the arguments to the generate array function. This is a length, which will be 10, and the generator that we just created. And then we call generate array of array int with those arguments. Seems sensible. That returns us an array. Look at that. It returns us something that has a start int and a len int and a buffer pointer. Clean. And then we do something here. We put that into a struct because that's the argument to this next function, the array len fun, for an array of array of int with that. Okay, that is pretty cool. That is pretty cool already. So we do generate array of array int. Let's look at that. Yes, that's up here. Generate array of array int, taking this one. So we extract the length out of the arguments. We extract the generator, which is the lambda. Then we allocate a new buffer of ints of the runtime known length that we were given. Clean. That's a pointer, yeah. And then we create this int 0, create this struct containing a cursor, and the cursor is the newly created 0, the generator, or the length is the length that we were given, the generator is the one that we extracted from the arguments, and then the buffer pointer. And then we call init array of int with that thing. Yeah, and then the array is just something that points to that now initialized buffer, has the given length, and starts at 0. Basically like a view of the entire buffer that we created. Clean. Now what does init array do? Let's look at that next. That would be somewhere here. Init array of array ints. Takes a struct that contains a cursor and a length and a generator. Sure. Wrapped in 0. I'm not sure about that one. Let's see, do we do that up here? I mean, those are, the memory levels of those are compatible, so that's not super bad, but still, it is unclean. Yeah, no, here we just call that directly with struct. Init array. Yeah, let's change. Oh no, that's fair. Oh, that is fair. Oh, I was thinking, that this was something similar to. Oh, where do we have that? This a struct that contains a field named 0, but something. But no, that's just we have that in every function to just note that the ID that the arguments are available under ID 0. All right, yeah, fair enough. So we get the buffer pointer out of there, we get the cursor out of there, and we get the length out of there. And the generator as well. Cursor, length, generator, and buffer. Okay, fair enough. Then we compare the ints, cursor and length, and we switch on that. If that is less, if the cursor is less than the length, then we still want to do something, otherwise we don't do anything. And then we'll just return. Okay, so this body here is kind of interesting. So here we get the generator body, we get the generator closure, and then we call that closure body, and we build the arguments and call that. Oh yeah, that's the lambda body. This is the argument struct that contains the closure pointer that we extracted from the lambda, and the actual argument, which is, oh yeah, the int, the index into the array, the index of the item that we currently want to generate. Okay, and then we store that into the buffer at the index, yeah, this result. And yeah, that returns an int because we are trying to create an array of int. So we store that int into the buffer of ints. Clean. Then we add 1 to the cursor and create new arguments for calling ourselves recursively. And this will have the cursor 13, cursor incremented by 1. The length stays the same, generator stays the same, buffer stays the same. Clean. That is clean. Yeah. Yeah. So one thing that is missing is, this is fine, init array, but in generate array, after that array has been initialized, we actually want to free the generator. That's something that we still need to do. So in the array build-ins, in generate array, boom, 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 yeah, we call that init array thing with the generator, and then we want to free the generator. So builder dot drop the generator. That is of the type, well, oh, I think here we need a yogurt type, yeah. Oh, that would be a yogurt type lambda with a yogurt lambda type. And I think that needs arguments and a return type, perhaps. It needs to be a list of yogurt types. Luckily there is a yogurt type int. This lambda is just given an int. Does it need something else? Yeah, return type. Return type is the item type. Because it returns us an item. Alright. Yeah, and this also needs a reference to the pesto because it may add other functions there. Makes sense. Makes sense. Okay. Oh man. Let's look at this again. Okay, so generate array. Yeah, that initializes the array and then it drops this generator from int to int. Yeah, index to an array item, that's correct. It just drops that. Nice. Okay, so I looked at this. Yeah, that is, I don't even know why that exists, to be honest. Oh, yeah, I do know, but nah. Yeah, this makes sense. Here we have the dropping of ints. Yeah, that decrement is the reference count of the pointer, or of the closure. And if that is 0, otherwise we don't do anything. If that is 0, then we free, we get the free pointer, and then we free that closure. Nice. And that is a pointer that points to this function, which loads the closure, which is empty. It frees that closure. And that's it. Alright. Nice. Then, what else? What else do we have going on here? We have in our main function, after generating an array, we then try to get the length of that. So we put the array into the struct, sure, and then we call the array.len function with that. Nice. And the array.len function is somewhere. Oh, this is, by the way, the Oh, this makes sense. Hang on. Every call to the lambda drops the closure. Yeah. And the lambda has an int, the index, and a pointer to the closure. We load the closure, which is empty, and then we drop the closure. Yeah, that does mean that every time we call a lambda, we need to pass it ownership to the closure. So let's look at that. Yeah, more specifically in this init array function. Here we do an indirect call. Before we do that, we need to dupe the closure, because we want the lambda just to be usable afterwards. So in here, before calling that, we need the closure, or the closure pointer. And we need to dupe that. So builder.dupe closure pointer. Nice. That is nice. Oh, and then we need the type of that, and so on. So let's just do increment reference count. Yep. Okay, so let's see. And here, init array. Yeah, we increment the reference count of the closure. Yeah, so that then this call drops the closure, but the closure is still available afterwards, so we can call the lambda again. All right. Pretty nice. Okay, so I analyzed this. I looked at this. I did not look at this, which is the next function that is called. What we do here is we have this thing. We have this argument, which is an array, sure. And then we put that into this called ArrayLen on that, I guess, with that being the array. Well, okay, I looked at all of that, and that, and that, and that, and this is the only, kind of the only mystery left. So here we do ArrayLen of some array. We get the array, perfect. We get the buffer, and we just drop the buffer, because we don't need that anymore. Then we just return the length. That makes sense. Now, dropping a buffer of ints, that's cool. We decrement the reference count, and if that is 0, then we do something, otherwise we don't do anything. So if that is 0, then we just want to free the buffer. So we need to drop the individual items. So we create a cursor, which is 0 initially, and a buffer, and we call drop buffer items of int, which is a weird name, to be honest. drop buffer of int items would be better, I think. Drop buffer items of something that's not a thing. Oh, it's in the cube drop thing. Yeah. Yeah, drop buffer type items. Better name. Alright, of that thing. And that is down here, where we iterate over the buffer and we get the length of the buffer. Yeah, makes sense. We compare our cursor to the buffer length. And yeah, if it's equal or greater, then we are done. We don't need to do anything. Don't need to drop any more values there. If it's less though, then we load the corresponding item from the buffer. Load item from buffer int that buffer, yeah, at index of the cursor, and then we drop the int. Alright, and then we add 1 to the cursor and call ourselves recursively until finally the cursor is equal or greater to the buffer length. Alright, and then we free the buffer and then we return from this, and then the array length function returns to the main function, which is here. It has now freed the array and we just return the length. Cool. Very, very cool. Yeah. Actually, you know what, I think yeah, let's enable more of the compilation pipeline and see how far we can go. So the waffle. This is where things will probably fall apart because we changed quite a lot. Pesto to waffle. Yeah, we no longer have call instruction. No, in the, I think. Now we have call built in. Yeah, depending on the built-in, we do different things. Perfectly sane. Alright. The cool thing is filled array and array get, and these are not like this. You see, this is super complicated. Not anymore. These are no longer built-ins. Instead, we just have new buffer. Okay. New buffer, which accepts a length. And how does that actually represent it then? Pesto, call built-in, some built-in, and then the built-in is pesto built-in, sure, which is defined here. Oh, we don't have buffers. All right, all that entire array stuff is just not here anymore. That is cool. Instead, the array operations, they operate like they are completely new instructions here. Yeah, all right. For example, the new buffer thing is a pesto new buffer, and that has an item type and a length. All right. That's just new dot item type, and let's maybe move that, you know, new array, yeah, that's filled buffer thing down there. I know that's not an exact match of the logic, but it will give us a nice starting point. Hang on, we do have, what's the order of things? We have new and load and free, and then this buffer stuff. Alright. So let's do that similarly here. We have new and load and free, which is for some reason down here. New and load and free, and then we have the buffer stuff. New buffer, get buffer len, just args, I think is fine. Yeah, that will be similar to ArrayList actually. Well, no, maybe not really, I don't know. Yeah. Get buffer len. Then we have load buffer item. Let's call that load, and that will be similar to the array get up here. Yeah, then we have store buffer item. Alright, then we have free buffer. That contains pesto free buffer, sure. Yeah, these stay the same, although they have different names. So there is no longer dupe and drop, but there is increment, reference count, and decrement. And dupe and drop are really just operations that semantically, you know, work on values. And there's get reference count of some pointer that will just load the pointer. Load 8 bytes from the pointer. Yeah. Nice. And then what else? No, we don't need to handle that. Slices, we don't need to handle that either. Concat strings is also not pesto built in, I believe. Oh, it is. Let's remove that. That should be desugared into something. I don't know yet. Strings are also broken right now, so. Alright. So, we have that. Yeah. I mean, this is actually quite readable, you know. Not so much clutter in there. Cool. And I wanted to copy that to the array built-ins. Copy array get, yeah, and set. And then also array slice. thought maybe, just maybe, this code might be useful. But probably not. So let's just comment a lot of that stuff out. Like that. And then just do, I don't know, finish with nothing. Not correct, I know. But this isn't even used, so that's fine. Alright. Alright. Now let's go through these. Because these will become much simpler now. If we want to create a new buffer of this item type with this length, yeah, on the heap we allocate space for the data with the following layout. Look at that. First the reference count, then the length, and then the individual items. So we do a waffle malloc. Of the, well, item type memory layout size. Hang on. Hang on. Let's build the stride size, which is the size rounded up to a multiple of the alignment. So that would be item type. We memory layout that. We take, well, yeah, item layout, I guess. Item stride size is item layout size round up to, not power of, but multiple of the item layout alignment. I could build something better for that. Let's maybe go into here. Yeah, memory layouting something returns us that. Yeah, and then we'll have some sort of stride size on a memory layout that returns us an int, and that is just the size rounded up to a multiple of the alignment. Alright. So we can just do item, just do stride size is item memory layout, stride size. Alright, and then we add 8 for the reference count, 8 for the length, and then we multiply the length that we want with the stride size. Alright, yeah, then we store a reference count of 1 and the length, and then we don't need this. Which is pretty amazing. Yeah. Perfect. And then we just return the pointer, and that's it. Yeah, that's cool. Then getting the buffer length. That's gonna be simple. And get buffer len. Let's see. Get buffer len of some ID. Well, we just of some ID. Damn. So we can just do, so we are given a pointer basically to the buffer. And then we can just do waffle load. Ah yeah, let's do builder.local of some waffle load. But then again, maybe not, just waffle load of the pointer plus something. So a waffle add of the pointer, we add 8, giving us the offset of the length. And then from that we load 8 bytes with an alignment of 8. And that's it. That's everything. Really cool. Then loading a buffer item. Yeah, we have a load, and the load has a pointer inside. Let's see. Pesto load buffer item. It has a buffer pointer. It has an item type and an index. Alright. So, it has a pointer, that's just load.buffer. It has an index, that's just load.index, and it has an item type. Yeah, no need to worry about that. The array get and set functions, they already do the bounds checking, so we don't need to do anything here. Pretty cool. Yeah, we don't need to drop anything, like everything is, the whole management stuff around that is done for us. We only need to actually get the item. So that would just be a waffle store, I guess. Let's say item layout, maybe. And that would be load.item type memory layout. Yeah, and then waffle load of the pointer, which would be load.buffer. Yeah, I think this is a bit clearer. Waffle add. Yeah, we have the buffer, we add 16. And then we add the start. Nope, no longer needed. We just add the index. Oh, not quite. And yeah, we do load a single item, so this needs to use the stuff from the item layout. This, however, needs to be multiplied, the index with the the strike size of the item. So this would be waffle mul, I guess, of the index and a waffle int that is the item layout strike size, just like that. That is clean, super clean. All right. That's everything needed for loading an item. And storing an item will actually be, well, pretty similar. Very similar, actually. We still calculate the item layout, we just do a waffle store instead of a load. And yeah, this will have the same, buffer plus 16, and then the index multiplied with the item layout stride size. I think waffle store just needs the item as an additional thing. And that would be store.compile or something. No. Mapping.get. Store.item. Oh yeah, same thing here by the way. Store.these and also mapping.get. And these also need to be mapped because we are interested in waffle expressions, not in just doing anything in IDs. Item layout, yeah, that is store.item type memory layout. And here we need an extra comma. Alright, yeah. Then finally freeing the buffer. Then is actually exactly that. What we did for get buffer then. Yeah, we have the len, we have the memory layout of an individual item. And well, then the size is just multiplying the it's an add. Here we have the reference count and the length in the beginning. Then we have several items. Oh, actually that's like pretty similar to this one, which totally makes sense. Like to this one. Yeah, exactly this. That's crazy. Yeah, let's structure this similarly to the other ones. So let's just calculate the item layout. And then here do item layout sprite size, and in here do mapping dot get the len, and just wrap that on multiple lines. And we're at 16, and with that, yeah, perfect. Nice. Then, yeah, down here we'll have something similar. Something very similar. Yeah. Reload the length. We calculate the size in bytes. And then we free those bytes. So that would be waffle free. Oh yeah, I think you shouldn't really like, you know, return side effectful waffle expressions. So let's not do that here and here. loading installs being considered side effects. So. Alright. Cool. Cool. Okay. Yeah, and then we free stuff, and that needs a pointer and a type. No, free buffer. Hang on, that's what we are doing currently. Let's see in the waffle what goes on here. It's a pointer and a size. That would be free pointer, so mapping dot get free dot buffer, I guess, and the size. Cool. Yeah, that has a side effect set. No, just to be sure. Then doesn't exist. That is correct. Creating a new buffer. Oh, hang on. Then does. Oh, I see. Yeah, I guess if we use that multiple times, let's just do that. So here we have an ID probably. Yeah. Oh, doesn't need that. Which makes sense, because it can figure out the alignment from the item. Yeah, this is just free item type. This is, yeah, sure. Pointer is mapping get free dot buffer, and then in here just free the pointer. Alright. Get a reference count. This call doesn't work. Waffle load of some ID now. yeah, let's look at the optimized version. I think that's easier to reason about. So that would be here, this one, not that one. Okay, I mean, these are kind of, sure, just calling some functions. What I'm interested in is actually creating the array and getting the length and so on. So those that interact with the buffer, the built-in functions. Let's just go through that. We have generate array of ints. Okay. And just the malloc part. So here we allocate memory. By adding 16 and the length, probably, of the arguments with 8. And multiplying that with 8 because one int is 8 bytes in size. So we multiply the length with 8, we add 16, we add that, we allocate memory for that. And then we store in that a 1, and then in that plus 8 we store the length. Okay, yeah, and then we init that drop stuff. Sure. Then the other array functions, init array just stores to the array. Yeah. Let's see how that works. These are like checks, I think. And this is the actual store. So we store into somewhere. Now what's going on here? We take the we take 0, which is the arguments. Yeah. That 16 to 24. Okay, that's probably the array. I think so. Not sure about that one. Oh, this is given like the the start cursor and the current cursor and the length and a buffer pointer and stuff like that. So okay, sure. And then we get some member, that's probably the pointer, sure. And we load stuff. What's going on there? Oh, I see. Oh, this increments the reference count. Oh, of the closure. Ah, that's why this is 16 to 24, because that's size 24 is a lambda consisting of the body function pointer and the closure pointer and the free function pointer. All right. This is weight formatting. Need to fix that. Yeah, we call that. I'm interested. Oh, this just calls the lambda, and this is the actual store to the array. All right. So here we store the returned item, the returned int, into the array at this position. adding the base pointer of the buffer and 16, and then also adding the offset within the buffer, which is the multiplication of the index and a single item size, aka 8 bytes for instance. Alright, cool. Yeah, we have dropping, we have freeing, we have more dropping, okay. ArrayList. Oh yeah, this. Seems reasonable, maybe. I feel less confident than in the previous one. Just because it's a bit more cryptic and detached from the source code. Yeah. This one right here. It drops the buffer. Okay. Yeah. This is the free. Okay. Nice. So this just calculates the size, I see, and then frees the original pointer. Alright, alright. I am wondering about getting the size from an array. Haven't seen that. I mean, yeah, from an array, but not from a buffer. Oh, I guess because that's not even needed. That's not used here. Yeah, that makes sense. Okay. Yeah, then that to ground probably doesn't work. Let's see. Because we have new... Oh, that does work. Sure. Oh yeah, because it's just stalls, you know, loads and stalls and so on. I guess, yeah. So then we can just return that. I think I'm gonna stop there for today because still have other stuff to do. Alright, and it just returns 10. That's perfect. What? That is crazy. Yeah, I mean, it's still not completely finished. There is slices is something we still need to do, and testing, you know, getting stuff from an array. I think also setting stuff in an array. I'm not sure about that one. Array built-ins. Yeah, some of these need to be fixed or implemented in the first place. Yeah, generating an array works. Getting the length of an array works. Getting an item from an array also works. But setting an item, well, there's still, you know, that works if the reference count is exactly 1, then we'll just store the item in there. But here there's a bit to do. And also for slices, there's a bit to do. yeah, I'm just gonna do that, and then I think this is done. But for now, see you sometime. Alright. So the only thing remaining is array slice and array set if the reference count is greater than 1. So let's go with array slice first and then figure out the rest. Yeah, here we take an array, I guess, and a range, which will be actually a struct that then has a start, which will be an int, and an end, which will be an end. The start is inclusive, the end is exclusive. Yeah, and that's it. It takes 2 parameters. Alright, so what we do is we basically do this. We get the arguments, we get the array out of there, and we get the range out of there. Yeah, we need to check that the range is within bounds. So let's just uncomment this code here and adjust that. First we'll need to check that the range start thing, so range dot let's just extract that up here. Range dot start is builder dot member of range with the name start, same with end. Okay, and we'll need to make sure that the range start is larger or equal or greater than 0. Otherwise, we say, oh, this is not valid. Range start out of bounds. And then we'll need to check that the range end is actually less than the array length. Yeah. Okay. And then we actually don't need to touch the buffer at all. I think. No, not even for the reference count, because this compile array slice function is given, one array is given ownership over one array, and it returns you a new array to that same underlying buffer. So the reference count of the buffer doesn't even need to be adjusted. Alright, so we just create a new array, with some stuff inside. Yeah, and we're gonna figure that out. So what do we have here? Range and range len. Oh, yeah, true. We actually need to check the range length. Compare that to our length, I guess. No, actually this is fine, I think. Like if you have an array that has the size 10, and your start is 3 and your end is 7, the start doesn't matter for the range, for the end to be valid. The end just has to be less than the original array's length. Yeah, no need to calculate the range length and stuff like that. Okay, what do we do here? We also just have some assertions. Yeah, and then we kind of build this aggregate. In our case, we would build a new struct with a buffer and a start and a length. That's what we need. So let's do that. Let's say builder.struct with a buffer and start and a length. All right. That's pretty cool. Then the buffer is the same as our buffer, so that's just build a member of the array, the buffer. The start similarly is going to be the start of this plus the start of the range. So builder.add ints of the original start and the range start. Maybe that even fits. Yeah, that fits on a single line. Beautiful. And the length will just be the length of the range, which will be sub-ints of the range and the range start. Clean. Alright. Boom. I guess that's it. And then we finish with the new array. Yeah, sub-ints is not a thing apparently, that's fine. And also I'll need to add locals for these. Builder, somebody, builder. Builder dot local. Actually, I'm not sure if we do that correctly for the other, the other functions. Hang on. Oh, I think we don't need locals. Locals were a thing from the waffle. Yeah, okay. Okay, that's pretty elegant. So let's look at the builder and add a sub-ints function, similar to add-ins, but just for subtracting integers. Sub-ins nice. Let's look at the. Let's actually use that, so in the playground. Yeah, we generate an array. Now let's take a slice from that. A slice from 1 to 5. And yeah, we need to import that. Slice that takes an array of t and a range of int. That means we need to know what a range is. Range of t and int is already imported. And also the to function for constructing a range. Array slice to pesto. Oh, I see. So this would be in the mod, corresponding mod file, where we need to call this function now. these compile functions, they this one accepts a length and a generator. This one accepts an array. This one accepts an array and an index. That's clean. This one accepts 0, 1, and 2. Let's turn that into an array and an index and an item. Yeah. And then in here, let's turn that into an array and a range. All right. Okay, so we need an array and a range, and then we compile the array slice function, and we call that with the array and the range. That returns us another array. Perfect. Yeah, strings are not supported yet. That's very true. And actually, I don't want to support strings right now. I want to support them. I want to build strings based on arrays. Basically, have something that, like an array of bytes or something, and just build a string in the standard library, not provide that from the language itself. Yeah, but I don't want to do that right now in this video and follow up. So yeah, not quite sure what to do about that. Let's maybe where's that in string? Compile array slice, that compiles, that uses builder.string. Yeah, I see. You know what, for strings, let's just say that this is something similar to arrays, I guess. You know, just having the bytes, UTF-8 bytes. Some field in there that tells us, well, these are the bytes of the string. And that's just going to be a pesto array type. Right, so we need to create an array somehow. Ooh. Yeah, let's just use some pointer and length. Let's just say this is pesto object. Build.push of pesto object struct that then has a buffer, which will be some pointer, let's say a null pointer. Pesto. Now we can just do pesto op.int 0 of the type. Yeah. This is supposed to be that, I think. Yeah, no, yeah, this yeah, a null pointer, which let's just hope that, I don't know, you can only use this with valid indexes. Also, a start will just be 0, I guess. Builder.int 0, and end will also just be builder.int of 0. So yeah, this is actually a valid string, I guess. Just some array with a buffer, a start, and an end. But the string has the length 0. Alright. Oh, well, let's... I want to add a to-do there. Well, that is interesting. We're converting some pesto expression to waffle. Yeah. And let's just print that, I guess. Pesto to waffle. In here, for every expression that we lower, let's just print the expression. Waffling that expression. Okay, yeah. Debug version of that, sure. Okay, so we have this crash built in. Yeah, so far so good. With an argument that is some other expression, sure. So for the crash built in, what do? We do this. Waffle crash with the first argument and the second one. No, crash should just take a single argument. The message. Yeah. No, just takes the message, and then that is an aggregate that contains, the pointer and length. Let's say this pointer just checks the size, I think. Let's check that the size is 16, crash button message is not a string. Oh, look at that, it just creates a waffle aggregate. Yeah. Alright. Why not? Oh, hang on. This is a string. And a string, as we established, is basically an array of bytes. Which means it's actually 24 bytes, because it contains a pointer to the underlying buffer. But because we want to get efficient substrings and so on, there's actually the start of the entire buffer array. And then it also has a start, index, and a length. So 24 bytes in total. All right. Okay. Waffle switch. Oh, this is curious. Because all the panics, they have a nice message, even this one. But it just says, oh no, the program panicked. Without any reason indicating why. That is bad. Let's see, we have some... Oh, it does, up here. Oh, and then these are the switch cases, I guess. Waffle, this waffle body. We have this other waffle body and yet another waffle body, okay. And each of these has locals, and it returns a waffle expression of size 0. Alright, this right here returns a waffle expression of size 0. And then this one returns a waffle expression of size 8. Huh. Okay, while we are trying to compile that build-in, that crash build-in. Maybe not while we are doing that. Oh, I see. If we have multiple branches in the code, for example, in here, this has a size of 0, and then this right here crashes, and this also crashes. On here, this has a size of 0, this has a size of 0, but this just crashes. Well, that isn't represented in waffle expressions currently. So crashes don't really, like diverging control flow crashes, they need to have some special handling because they are compatible with any other, size of the stack. Yeah, I don't know how to deal with that yet. Or whether I want to do that right now. I could just say arrays work, Sure, array. Let's maybe look at where that's happening. And this looks fine. You're constructing a message for the crash. Is there a switch in here? So let's look at every switch and just see if these have different lengths. Yeah, and here this finishes with nothing. This finishes with nothing. This finishes with nothing. All right. Next switch is in here. This finishes with a crash. This with nothing, this with nothing. This one finishes with nothing, this with crashes. And this one with crash, nothing, nothing. And here we have nothing, crash, crash. Nothing. Here we go. Yeah, I think crashing is compatible with the nothing type. But in this case, we actually, we want to return something, and that is not compatible with this one. Hang on. I mean, this makes sense. If the reference count is 1, then we do something. If it's greater, we do something else. But if it's 0, that can't even happen. So just put finish with nothing in there, but of course that's not compatible with these other 2 branches. Yeah. Yeah, not sure what to do about that. Change this to crash, diverge, so that the switch branches are compatible. Yeah, then we have this one, where this one crashes, this one is nothing, okay, then nothing and crashes, alright, but that's it. So I think as long as crashing is compatible with the nothing expression, that should work. Let's look at the builder again. So we have this crash built in, and that returns you a struct, an empty struct with size 0. Yeah, that should be valid. Like, that is exactly the nothing type. So I don't know. I don't know what to do about that. I think I'll just stop here. I'll call arrays kind of finished, at least the simple. Oh, hang on. Yeah, setting something in an array with a reference count larger than 1. That is not yet done. Yeah, but like this one. Yeah, and I want to implement this once we have. I mean, I can implement that, sure. Just can't test that. So if we have an array and the reference count is larger than 1, and we want to set an item in that array, that is interesting because now we can't just mutate the array in place. We can't just mutate the memory there because there's another reference to that same underlying buffer. And in Plum, values are immutable, like at least the semantics, under the hood. Again, this gets optimized if the reference count is 1. But in the general case, we need to copy the underlying buffer, or at least the part of the buffer that the array points to. So I think what we need to do here is we need to, what do we need to do? We want to copy the part of the array to a new buffer. let's do that. And that will be similar to, you know, this generate array thingy, this up here, generate array. Yeah, where we basically allocate a new buffer. Yeah, let's maybe add a comment here. So the reference count is greater than 1, which means that some other reference to the same buffer exists. This means we can't mutate the buffer contents in place. Instead, we copy the part of the buffer that this array points to, and then we set the item in that copy. All right. So we want to create a new buffer of the array length, not the underlying buffer length. We only want to copy the part of the buffer that this array represents. So I think we can do, you know, we have the array. Let's do builder.member of array the length. Yeah, like this. We create a new buffer, same item type, of our array length. Then we copy the array content over there. Yeah. Copy the array content. Let me take a quick break. Okay, I think I'll just add a copy function for arrays. You're copying from one array to another array of the same size. I'm not sure I want to like actually expose that in the language. This will just be an internal one. Similar actually to this init array fun. And it's also going to be recursive. So, okay, array set. And then we'll also have the, boom, another function, compile copy array fun with an item type, and this will be copy array of that array type. Okay. This will take, first of all, an array from, it's going to be a pesto array type, and a to array, which will also be a pesto array type. Yeah. Copy. I could also like just copy the work on a lower level, you know, copy buffers directly, pass buffers around here. Let's actually do that, I think. Yeah, so we have a from buffer, a to buffer, but then we need two cursors and so on. basically it's what we had above, but instead of a generator, we have a from buffer and then a from cursor. And we use that to generate items, aka copy out items out of there. Yeah, and then we can get the buffer, cursor length, and not the generator, but the from buffer and the from cursor. But you know what, let's make this consistent, and then let's call this 2, put the length at the back. And also let's maybe switch these around. From and to, here we have alright, I think we're slowly getting somewhere. Yeah, that looks fun. Copy. Fun. Yeah, copy buffers between buffers of, and then the item size. Nice. Yeah. So what we want to do is we check if the length is 0. Yeah. So we compare the length to 0. If it's less than 0, well, that can't really happen. So, nope. What is going on here? We call ourselves, there's the recursive case, basically. Yeah. You know, less can't really happen, so that's just that. Yeah, I'm just juggling these around, like so. Okay, if the length is less than 0, it can't happen. If it's equal to 0, we are done, we don't need to do anything. But if it's greater than 0, we still need to copy something. So then what we do is we only basically get the item from the from buffer, which will be pretty similar to array get actually, except we don't need to do the checks. Yeah, all these checks, we don't need to do them. Oh, hang on. Yeah, we just get the item like so. Let's see. Copy. Here we are. Yeah, the from offset is going to be adding integers. Yeah, the from buffer. Oh, hang on. There's load buffer item. All right. Of the from buffer, we have the item type, and the offset is going to be the from cursor. Fair enough. Yeah, that is the item, and then we dupe that item. And then we store that into the other buffer. That seems reasonable. So builder.store buffer item, and I think we don't need that. But we do that. So we have the to buffer, we have the to cursor, and then the item. I believe that's the way it is. Yeah, and then we don't need any sort of dropping the buffer, stuff like this. Oh, look at that. Yeah. Clean. Very clean. And then we just call ourselves recursively. So we have the from buffer, that's just going to be the from buffer. We have the to buffer. Oh. Oh, yeah. I guess. And then same with the cursors, but organized them like this. Yeah, from buffer and from cursor, to buffer and to cursor. And the cursors, they need to advance by 1. So something like this. And the length, on the other hand, that's gonna be subtracted. Like so. Alright. Yeah. And then we're copying over the items until at some point we don't call ourselves recursively anymore. That actually seems pretty cool. And that means that in here we can now call that function, which will be similar to calling the init array function. So let's copy that to the array set code in here. Yeah, we call the compile, was it copy fun, copy buffer, copy fun, that is very generic. Oh, by the way, in here, signature. Oh, yeah, our own signature, that's actually correct. Yeah, and then this is copy buffer fun, and this needs a lot of stuff. Item type, that's correct. So it needs a from buffer, it needs a from cursor, it needs a to buffer, it needs to cursor, and it needs the length. Now we'll need to figure those out. So we have, let's see, we have the original buffer from the original array. And here, let's call that copy buffer. I don't know. So the from buffer is going to be the original buffer. The start is going to be the start of this array. So that is array dot, the member, the start member of the array. So builder dot member of the array, the start. Then the to buffer will be the buffer copy, and there we start at index 0. And the length is going to be the array length, which, I mean, let's get that out of here. Why not? And in general, like, I think the start and end we need them here as well. And the length, we need that over here. Yeah. Alright, so let's maybe extract the start from the array, which is going to be array builder.member of the array, the start, and we'll have the end, and we'll have the buffer. Alright. Yeah, and here we check that the index is larger than 0. Here's here that the index is less than, look at that, the array length. Yeah. And then this, we already have that. Alright, this right here will just be the start. Previous one is loading that, dropping the previous item, storing the new item at that position. Okay. Here we get the length, we already have that. And then we call this with from cursor being the start. Alright. Yeah. Then we have, after this, the copy buffer contains a copy of the kind of slice of the array that we point to. So then we need to set the item. Still need to do that. And that would be actually quite similar to this one. Yeah, let's factor that out actually. So let's say this is array with ref count 1. And if it's less, like this can't happen. Yeah, the ref count can't be 0. But if they are equal, now let's add a comment above here. Kind of explaining the general thing. And if the reference count is 1, we have exclusive ownership of the, if the buffer's reference count is 1, we have exclusive ownership and can mutate the buffer in place. Otherwise, we copy the part of the buffer that this array points to, and then we set the item in that copy. Alright. So what I'm proposing is that we do this in the end, basically. Like down here. So here we just do, if the reference count is equal to 1, then this just evaluates to the array. Like so. If the reference count is greater, then we'll need to create a copy. So we do, builder.call, compile copy buffer fun, boom, and then we kind of finish with a new array. And that's going to be builder.struct contain the buffer, which will be the copy buffer, and the start will be 0, and the length will be the original length. We finish with that new array, and then this right here will be an array with the ref count 1. And then we can get the start of that. So that would be build a member of array with ref count 1 start. Also get the buffer out of there. Yeah, then we'll add the index. We get the item. We drop the previous one, and we store the item again, like the new item. Yeah, and then we finish with a new array. All right. Yeah. Yeah, still won't work, but at least the code is implemented. And the difficult thing is, like, there is quite a lot of stuff that I need to do. I need to, basically I want to support strings in the language based on, using arrays as the fundamental thing. And then I want to support crashes properly. But crashes kind of depend on strings. And arrays, well, they depend on crashing sometimes when they do the bounce checks. So it's kind of like this circular dependency of all these fundamental things. So I think arrays are implemented in principle. Creating an array works. Setting items and slicing an array probably works. I can't test that yet. But still, I think the main work for arrays is done. I'm going to stop it here, and then in the next video work on, I don't know, strings, or like bytes, the fundamentals for strings, then on strings, then on crashing, and then kind of revisit arrays and see if that works. So with that, that's it for this video. See you in the next one. Bye.